everyone, welcome to the course on medical biomaterials. We will continue on the topic of polymers. As I said, polymers are widely used as a biomaterial. Polymers are made up of repeat units of the one single monomer, or it could be multiple monomers, two monomers. So, there are wide range of polymers available which can be tuned for any desired application and with different properties. Okay, so, we will look little bit on the structure of these polymers also. For example, look at this polyethylene terephthalate, it is polyester, it is originally invented for making fabrics. Okay, so, it is called a polyethylene terephthalate. So, it has got a terephthalic acid unit here, okay. Then the ethylene glycol, that is how they are condensed, terephthalic and ethylene glycol condensed as the repeat units. It is called polyester. It is also called dacron. It is used in manufacturing vascular grafts, large diameter vascular grafts, 2 mm type. It is also involved in valves, patches, so many other applications. It is called polyester, and the ester bond as you know can be degraded with the esterase type of enzymes. Look at this nylon 6, this is called nylon 6. Okay. When we put N, that means there could be N could be a very large number. So, it is like this. So, it starts with caprolactam converted to nylon 6. It is used in sutures, and these sutures are not degradable, they are very strong. Nylon is used in applications where you read very high tensile strength. So, here those days they used to use it as sutures, but then they do not degrade. So, nowadays they have switched on to other biodegradable material. So, in a polymer you are going to have repeat units, that means same unit gets repeated hundreds, thousands of times, and depending upon the number of repeat units the molecular weight also changes. For example, polyester will have this particular repeat unit, C double bond O, okay, C double bond O, O, this is called the ester bond, and of course esterase type of enzymes can degrade this bond. Polyamide, it will have C double bond O N H, okay, and this is the repeat unit. So, it can have many of these actually. Okay. Please note the amide bond in the protein, that also has got a C double bond O NH2 or NH and some other functional group like aliphatic and so on. Okay. Polyamide protein. Polyurea, look at this. So, you have C double bond O in the middle of 2 nitrogen amines here. Polyurethanes, okay, these are very strong polymers, not degradable. Okay, we have CO on this side, C double bond O, and then we have nitrogen here. Polysiloxanes, look at this, Si, silicon is here, oxygen is here, and you can have different groups. Cellulose, COC and so on. So, these are the repeat units you will find in some of these polymers, no, it keeps on repeating many times. Okay, more of the structure. This is called polyparaphenylene, okay, because you have the nitrogen here, NH paraphenylene terephthalate. If you remember, this looks like your this, right, terephthalate. Here it is phenylene because you have the nitrogen, it is extremely strong, it is called Kevlar commercially, and they sometimes make a bulletproof vests with this. They are extremely strong and they have very high tensile strength. You can make it into fibers. So, we can make it like ions, and then we can spin it, okay, to make fabrics out of this. So, that is called polyparaphenylene terephthalate. Okay. So, this is the para groups, this is the terephthalate group, and then phenylene, nitrogen is there. Polyethylene, polypropylene, all these are very ubiquitous polyolefins. Polyethylene is very simple, CH2 here, CH2 here, keeps on repeating. So, depending upon the number of repeat units, the n number of small n, we can have low density polyethylene, high density polyethylene, ultra high molecular weight polyethylene, like that, you know. So, if you look at the molecular weight, low density around 10 power 3, high density 10 power 5, ultra high molecular weight 10 power 6. So, these are used sometimes in drain tubes. These are used in knee joints when they have a total knee replacement surgery to prevent metal on metal contact. You have this. Okay. So, in the low density polyethylene, sometimes instead of being linear, you can also have side chains. That means during polymerization you can have a lot of side chains coming in. So, obviously it will not be very compact. So, the molecular weight is low, the density is also low here. So, as you can see, the density increases, tensile strength also increases from LDPE to HDPE to ultra high molecular weight polyethylene, and they are very hydrophobic material because we have only carbon, we do not have anything else, we do not have oxygens and nitrogens. So, it is extremely hydrophobic type of material. Polypropylene. So, there is a CH3 here, okay. That is why it is called polypropylene. Density is low because this CH3 is a bulky group, so you cannot pack it up too much, but the tensile strength is also high better. So, polypropylene, there are different types of polypropylene where the CH3 and next CH3 can be in the same direction or same side or in the opposite and so on. Okay. So, they are called atactic, syndiotactic, isotactic, depending upon how the consecutive CH3s are located. So, this is called polypropylene. Again, this is also very highly hydrophobic because we have only carbons, we have nothing else, no oxygens or nitrogens or sulfurs. These polymers are used quite a lot because they are very cheap, easy to fabricate, we can make it into different shapes and sizes, okay, molded and so on actually. So, and they are very strong, so they are used in many applications as well, but remember they are very hydrophobic. So, obviously there could be biofilm formation, bacterial contamination and so on. Polyacrylates, okay. This is the general structure, CH2C, okay, there is a COOR. So, this is the ester part of it, and there is a R1 here, okay. If R1 can be H or methyl or ethyl, R2 can be methyl, okay. So, we can have methacrylate, okay, when we have methyl here, methacrylate, that is an ester. If you have a methyl here, methyl methacrylate, otherwise we can have just methacrylate if R1 is H, or we can have methyl acrylate but ethyl methyl acrylate. So, we can have different types of polyacrylates by changing this R1 and R2 group, but the most common is polymethyl methacrylate. That means you have a CH3 here and a CH3 here, okay. It is used quite a lot in dental applications, maxillofacial applications, bone, cement, acrylic, and then it has got fantastic light transparency. Okay, so it is used in many places where you need transparent observations, and PMMA has higher tensile strength than polymethacrylate. That means when R1 is H, that is called a polymethacrylate. So, PMMA is the polymer which is consumed a lot in biomedical applications, maxillofacial surgeries, dental applications. So, it dates back to a very long time, and it is easy to make the polymer starting from the monomer. When we apply a UV, the polymerization happens. So, it is very simple to make, and we can have different types of polyacrylates. Okay, next hydrogels. Hydrogels is polyhydroxy ethyl methacrylate, HEMA, hydroxy ethyl methacrylate. Okay. So, look at this structure here. Okay, so we can have hydroxy, then we can have ethyl, then methacrylate, okay, this methacrylate and so on actually. They are extremely hydrophilic, they are hydrogel. That means a hydrogel is something which can take in lot of water. Hydro is water, right. So, it can take in lot of water, they can swell a lot. So, it is used in soft contact lenses, they have got a good oxygen permeability. So, it is used in soft contact lenses, so person can wear it for a very long period of time. Whereas, if you look at PMMA, it is used in hard contact lenses also, because it has got very good transparency, but it does not take in as much more water as this particular HEMA. is called polyhydroxyethyl methacrylate. Okay. So, hydrogels not only used in soft contact lenses, they are also used in wound dressing, surface wound dressing. We can even encapsulate drugs and so on actually. Now, other polymers, these are some polymers which have been approved by the Food and Drug Administration USA. Polylactic acid, PLA. So, we have this type of structure, okay, lactic acid. So, how does it, it's a biodegradable, is FDA approved, but it's insoluble in water. Now, how is it made? Ring opening polymerization of a racemic mixture of L and D lactides to produce poly-D-L lactic acid. But if I take only L lactide, then I will get PLLA, poly L lactic acid. Okay. Okay. So, they are insoluble in water, and so we can tune their properties by either taking a DL racemic mixture of lactides or just L lactide and so on actually. PVA, polyvinyl alcohol, it is a water soluble polymer. This is also approved by the FDA, okay, and it is also very hydrophilic. So, it is used in eye drops, and also it is used in hard contact lenses solution as a lubricant. Okay. So, PVA is a very good lubricant because it is water soluble, it is hydrophilic in nature. Okay. So, it is used in such applications, and sometimes when I am mixing a hydrophobic polymer with the hydrophilic polymer, we use PVA to enhance the mixing properties. Okay. PLGA, polylactic glycolic acid, polylactic. So, we can have different combinations of lactic and glycolic. Okay. So, the structure is like this. This is the lactic part of it. Okay. If you can see this is the lactic part of it, and this is the glycolic part of it. Okay. It degrades by hydrolysis because we have the ester bond. It is also used quite a lot in medical applications, grafts, sutures. So, nylon sutures are not degradable. So, after the wound heals, surface wounds, the doctor has to remove it, pull it out, whereas PLGA type of sutures are biodegradable. So, automatically they will get bioresorbed. They can be used in implants, prosthetic devices, surgical sealant, making nanoparticles and so on. So, PLGA is also widely used, and the beauty is we can change or modify their biodegradable properties by modifying the lactic to glycolic acid. Okay. So, glycolic is more faster biodegradable than lactic. So, we can tune that. Then is polycaprolactone, and this is also biodegradable polyester. So, how is it made? You take epsilon caprolactone with a catalyst like a tin, we can make this polycaprolactone. This is also approved by FDA. It is a biodegradable, it is used in drug delivery device sutures. Okay. So, we can make PCL based sutures. Remember, there is something called polycaprolactam. Okay. That is almost like nylon, it is very, very strong, not degradable, but this polycaprolactone is degradable, it is approved by FDA. So, do not confuse between lactam and lactone. Okay. Lactone is a biodegradable polymer. So, a lot of polymers. Then comes PTFE, polytetrafluoroethylene. It is a very, so you can see fluoro, lot of fluoros here. Okay. Very crystalline, high density, low modulus, low friction coefficient. So, it is used quite a lot, it is very inert, so small diameter vascular graft. So, if I am looking at large diameter 2 mm, I may go for polyester. If I am looking at small diameter vascular grafts, I will go for PTFE. So, PTFE is used in vascular grafts, PTFE is used in BT shunts. So, this also has quite a good set of applications. Okay. So, we looked at a lot of structural features of different types of polymers used, and of course, PVC, polyvinyl chloride, is another polymer where we have one chlorine, 3 H's, okay, hydrogen, 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 one chlorine there, Okay. So, polyvinyl chloride is also very inert, it is used for short duration application. So, maybe drain tubes and so on. Okay. And because it is very inert and it is not used for many other purposes, especially if you are looking at okay, tissue engineering type of application. Okay. So, what are the applications? I have been telling PMMA, good light transparency, so it can be used for hard contact lenses, intraocular lenses, it is very stable. HEMA, hydroxy ethyl methyl acrylate, soft contact lenses. Polyethylene, high density polyethylene, tough, low cost, tubing, drain, catheters, acetabular components for artificial hips, knee joints. Polyvinyl chloride is hard and brittle, it becomes flexible by adding plasticizer. So, it is used in tubing for blood transfusion, feeding, dialysis. So, it is not used for long applications because the plasticizers present may come out. PLGA, absorbable, resorbable surgical sutures. Polyurethanes, okay, pacemakers, vascular grafts, heart assist balloon pumps, it is almost like rubber, it is very flexible. Okay, so, polyurethane is also finding quite a lot of applications. So, polymers, the ease of manufacturability to produce various shapes, tailorable properties. I can change, I take PLGA, I can change the amount of lactic to glycolic, I get different properties, reasonable cost. We can make it in different mechanical and physical properties. Okay, we can make it in different shapes. Later on I am going to do some experiments and show you. Disadvantages, leachable, there could be some monomer, like for example acrylic acid present in PMMA may leach out, which could be toxic. For example, any other monomers or leachants, for example if you take PVC, the plasticizers like phthalates are added to make it soft and flexible, that may leach out over a long period of time. Wear and breakdown, so they can wear out, they can also break down, there could be some oxidation reaction or hydrolysis. Difficult to sterilize, so if I use for example steam sterilization, some polymers may absorb moisture. Okay, if I use some chemical ethanol or something, there could be some reactions in some cases. So, we need to be very careful what type of sterilization method do I follow when I have a polymeric biomaterial. Okay. So, some other problems, polyethylene, it absorbs lipids, LDPE, so tensile strength becomes poor, high density ones are inert, so no deterioration occurs. Polypropylene, generally no deterioration. Polyvinyl chloride, tissue, that is rigid ones, tissue reaction, the plasticizers like phthalate present may leach out, material can become brittle. Polyethylene terephthalate, okay, so hydrolysis, because they have ester bond, hydrolysis, so strength can come down. Polyamides, nylon, they can absorb water, irritate tissue, lose tensile strength. Silicone rubbers, no reaction and very little deterioration. PTFE, solid specimens are inert, if it is fragmented into pieces it can cause irritation. Polymethyl methacrylate, rigid form, crazing, abrasion, loss of strength, heat sterilization. Okay. When I heat it for sterilization it lose strength. Cement, high heat generation, okay, when you make the polymer, unreacted monomers may leach out and damage tissue. So, each polymer has some problems or the other that is happening. Okay. Okay, let us look at how they are synthesized. There are two ways, one is called the addition, another is called the condensation. Okay, in condensation is also called stepwise. So, we can stepwise grow the polymer. Addition means we take 2 units and add them. Okay, so, polymers you can make like this with general structure like this, So, how do we do it? In the addition, radicals are formed initially, you generally add some free radical initiators, that is RO dot means it is a radical. Now, this radical reacts with this portion of this, it produces the activated monomer. Now, this keeps on growing, this is called propagation. So, grows, that is why it is called a stepwise addition, grows and then you terminate it, you add some terminating agent or radical scavenging agent. So, the polymerization stops and the chain growth stops. that is called addition polymerization. So, here generally it is through radical. So, you had a radical initiator which produces radical of the monomer and which keeps adding stepwise. Okay. So, the polymer grows, and when there is a radical scavenger, the radicals stop. So, the polymerization gets terminated. This is called addition polymerization. The next one, condensation. Okay. So, we add 2 units get condensed together, and generally you throw out water or methanol which is removed by using vacuums. Okay. That is how polyesters are produced. Like I said, terephthalic acid and ethylene glycol. So, you get when you use terephthalic acid, you get okay, methanol that is getting produced. Similarly, polyamides, proteins. So, all these are called condensation polymerization. Okay. How when you have functional groups on both sides, you can have condensation. See, for example, COOH is a functional group OH. So, we can keep on adding one unit with another unit and so on. So, monomers which have functional groups on both sides can be done through this condensation polymerization, whereas in the other one, stepwise you need to generate radicals which keep on adding and the chain growth takes place. Okay. So, two basic methods by which most of the polymerization reactions happen. We will not go too much into it, but it is good to know. So, we can have different type of architecture, linear, branched, like low density polyethylene starts getting branched, that is why the densities are low. Okay. Whereas high density will have less branch, so they get packing better, so the densities are high. Cross linked, so we have one unit, one chain, they are all cross linked like this. Okay. Sometimes we add a cross linking agent. Network, so we can have polymerization taking place like a network, dendrimers they call it. Okay. Star polymers, there are so many types which are in that fashion. Okay. The network type of polymer. So, different types of structures are possible, and they all have different melting points, different phase change temperature and so on actually. Okay. The properties also change because of these architectural features. And in the monomer arrangement, say suppose I have one unit, okay, another this is a homopolymer. Copolymer is when I have more than one monomer AB. So, I can have random copolymer, alternating copolymer, as you can see AB, this is random, or block copolymer A, B, then again A. So, each of this will have different set of properties change dramatically whether it is block or whether it is random. Okay. So, and it is possible to tune their reaction so that we can get either random or alternating or block copolymer. Of course, in homopolymer you will always have A. Of course, you may have branches like polyethylene LDPE, but this type of monomer arrangements will happen only when you have more than one monomer. Okay. There is something called toxicity, that is the arrangement of substituents around the extended polymer. For example, you take polypropylene. Okay. So, there is a CH3 there, right, at the pendant. So, the CH3 of one and the CH3 of the next repeat unit, if they are all in the same side, that is called isotactic, same orientation. Okay. If they are alternating, they can be syndiotactic, and if they are in the random fashion, you can be atactic. Okay. This happens especially when you have this type of extended functional groups or pendant groups. Okay. For example, let us look at this. Okay. Let us look at this PVA. Okay. They all the PVA OH of the next they all could be in the same direction, or they could be alternating, or they could be in a very random fashion. Same thing with the polypropylene. Look at this, CH3 of the next could be in the same direction and so on, or they could be in the alternating, or they could be in the random. So, these are typical examples. So, we can have all in the same direction isotactic, alternating syndiotactic, and this could be atactic. Okay. So, polyvinyl alcohol, the OH groups, or polypropylene, the CH3 groups. Okay. So, all in the same direction. So, again the properties change dramatically depending upon how the tacticity look like. Okay. So, you can see that is why polymers are become very useful in material applications. There are so many variations that are possible. The arrangement of the monomers, the 3-dimensional feature which gives you this tacticity. So, all these, that is the arrangement of the substituents. So, all these make a lot of difference in their physicochemical property. Polymers also have some crystallinity. They could be amorphous or semi-crystalline. They can never be completely crystalline, unlike your metals. Okay. So, they will be amorphous, semi-crystalline. So, there could be some amorphous region, some crystalline region. So, if there is degradation, the amorphous region may get degraded. Okay. Crystallization enhanced by small side groups and chain. Atactic polymers are always amorphous, okay, as you can see, and they cannot pack well, hence they are always amorphous. Isotactic may crystallize if conditions are favorable. Okay. Polymethyl methacrylate, polystyrene, they are all amorphous polymers. Polyethylene, polyethylene terephthalate, that is the polyesters, they can have crystalline properties. Okay. Polymers have 2 types of molecular weights. In fact, they can also have 3 types of molecular weights. Mostly one is called the number average molecular weight, it is represented as Mn. Other one is called the weight average molecular weight. Number average molecular weight, total weight of all chains divided by number of chains. NiMi, that means some chains have certain molecular weight, some chains have another molecular weight. So, you multiply and sum it up divided by number of chains, that gives you the number. Okay. Weight average molecular weight, that means we do not look at the number, we look at the weight of chains which have certain molecular weight. Okay. So, WiMi divided by Wi, understand. So, here we look at number of chains which have certain molecular weight, here we look at the weight of chains which have certain molecular weight, and number average is always less than weight average. So, look at this, suppose you have, because polymers will have a mixture of molecular weights, that is mixture of length. Okay. There could be some chain length smaller, some chain length longer, some of them very long. So, it will theoretically sort of follow not exactly a Gaussian distribution, but this sort of distribution. So, this will be the number average, the weight average. So, weight average will always be larger than the number average. So, if you divide weight by n, weight average by number average, that is called polydispersity. That means how dispersed the system is. It can be 1.2 or 1.3 and so on, because weight average is always larger than the number average. Lower the molecular weight, lower the transition temperature, viscosity and mechanical properties. Okay. So, lower the molecular weight. So, small molecular weight polymers will have lower viscosity, lower mechanical properties. I said there is third molecular weight, that is called viscosity average molecular weight, that is based on viscosity of different chain lengths. We will not go into that. So, generally everybody follows number average, weight average. Number average tells you the number of chain which have certain molecular weight. Here the weight of chains which have this molecular weight. Okay. That is how it is calculated, and I said weight average is always larger than number average. If you divide this MW by Mn, we get a term called polydispersity, that is generally 1.2 or 1.3 or 1.4 and so on actually. Then there is something called the degree of polymerization. Okay. That is number of repeating units, number average molecular weight divided by molecular weight of the repeating unit, that is called the degree of polymerization. This is obvious, right. So, one repeating unit, this is total molecular weight. So, if I divide this by this, it will tell you how many these units are there, that is why it is called degree of polymerization. As I said, polydispersity or heterogeneity, that is MW by Mn, okay, sorry, measures the polydispersity, heterogeneity of sizes, okay, Natural polymers are monodisperse, synthetic polymers are mostly polydisperse. Okay, mechanical properties, we have the strength, stress required to break the sample. We have studied long time back, tensile, compression, flexural, torsional impact. Okay, when you have linear, lower than branch, cross-linked network. So when you cross-link, they will have higher strength. Okay, when there are network, they will have much higher mechanical properties. So what are the factors which affect strength? The molecular weight. Cross-linking, if they are very highly cross-linked, they are going to be very strong and tough. Crystallinity, if they are crystalline, then you have certain better mechanical properties as against very amorphous. So molecular weight, tensile strength increases. Okay, increase in molecular weight, increase in tensile strength. Percentage elongation to break, that is the ultimate elongation. Originally I talked about thermoplastic, thermoset, right. So elongation to break tells you about the ductility, percentage change in the length of the material before fracture. So if you keep on increasing the length by pulling, it reaches certain length and then it breaks. Okay, that is the elongation to break. It is a measure of ductility. So thermoplastic greater than 100, thermoset less than 5, because thermoset is very rigid, it breaks. Okay. Young's modulus, this you know, long time back we studied tensile stress by strain. Okay, it gives you a stiffness of the material. So polymers also will have Young's modulus, but of course they are much lesser than metals like stainless steel. Okay. Toughness, there is the energy absorbed by the material before it breaks. Brittle polymers, high Young's modulus. Okay, like your even like your ceramic. Elastomers, low Young's modulus. Okay, ductile materials will have like this. Okay, so you have brittle polymers, ductile material, elastomers. This is a stress strain diagram. Okay, the slope, as you know, in the elastic region is called the Young's modulus. You remember all these, right, long time back. So the area under the curve gives you an idea about the toughness. Okay, so these elastomers, the brittle material, ductile material, that is toughness. Okay, before it breaks, right, from elastic to plastic region. Viscoelasticity, we again defined it long time back. Okay, we can have a elastic and the viscous. The elastic material deforms in proportional to the stress. Okay, so for example, returns to its original state when the stress is released. Okay, so I give at time certain stress, so the strain is here, until the stress is maintained, strain is here. As soon as the stress is released, it comes down. Whereas viscous material, okay, it takes longer for it to reach that value. Unlike, viscoelastic material, it slowly reaches and then it comes down, but it never comes down and reaches the, that is called the visco. Elastic material deforms in proportional to the applied stress and returns to its original state. Viscous fluid deform permanently by an applied stress and continues to deform if stressed again. Polymers have both elastic and plastic depending upon temperature and strain rate. At low temperature, high strain rate, elastic behavior is observed, and at high temperature, low strain rate, viscous behavior is observed. So we will see the viscoelastic type of nature of polymers. There is something called thermal properties. Okay. Polymers have this glassy state, rubbery state, and also the glass transition temperature. We will talk about all these in the next class. Okay. Thank you very much.